So in our previous lecture, we studied about molecular dynamics with the help of a example of liquid water. So what is molecular dynamics? And we discussed a little bit about the about its basic foundation. So the basic foundation of molecular dynamics is statistical mechanics, or we can say the classical form of statistical mechanics. So what is statistical mechanics? It's very important to know. So statistical mechanics is nothing but provides connection between macroscopic and microscopic nature of the matter. So what is the macroscopic and microscopic nature of the matter? It is defined by a state of that particular system. So if I talk about the macro state of a system, so macro state of a system is defined by macroscopic properties like pressure, temperature, energy, volume, density, etc. So whatever the system is, it can have a pressure, it can have a certain value of temperature or energy. So whatever it is, it is called the macro state of that particular system. And micro state of a system is nothing but ways of achieving a particular macro state. So there can be different possible ways of achieving a particular macro state, and I will clarify it through an example in the next slide. Let us consider that look at my pointer. Let us consider that this is a isolated system. So this is a isolated system. The system cannot interact with its surrounding. Okay, it is isolated from it. So we have n is the number of particles in the system, v is the volume of system, E is energy of the system. So let us consider that there are three particles in the system, and energy of the total energy of the system is 6 joule. So now what we are going to do, we are going to divide the energy of system between three particles. We are going to divide the 6 joule of energy between these three particles. And there is an exception that you have to remember, that no particle can have zero or negative energy. So we are not going to assign any zero or negative energy to the system. Let's do it. Look at my pointer. Here is number of particles are 3. Energy of the system is 6 joule. This is our isolated system. And remember the previous exception, no particle can have zero or negative energy. So the first possible combination is the three particles can take the same amount of energy, that is 2, 2 and 2. And the possible number of possible ways of doing it is only one. Okay, you can arrange the 2, 2, 2 and only in one way, that is written here. And if I, so first particle will take 2 energy, second will take the same energy, third will take the same energy. And talking about the another possible combination of 1, 2 and 3, so if first particle is taking the 2, third taking 3, and the last one is taking 1 energy, and what is the other possible combination? First particle can take up 3, second particle can take up 1, and third particle can take up 2. It's like 3, 2, 1, 1, 2, 3, 2, 1, 3. So there are 6 possible ways we can arrange these numbers. So, and all of them are adding up to 6. Okay, you can see here. So all of are adding up to 6, that is 6 joule of energy. So there are 6 possible ways of arranging all these numbers, these three numbers. Okay, and if I talk about the 114, then there are only 3 possible ways of arranging 114, that is 411, 141, 114. So they are the number of different possible ways we can achieve the 6 joule of energy by summing them up. Now, what is energy of the system? So, energy of the system is summation of number of particles with same energy multiplied by energy of the particles. So, if you see here, there are three particles with the same level of energy or with same energy, that is 2 joule. So energy of total energy of the system will be energy equal to 3 multiplied by 2 equal to 6. And if I talk about second configuration, so the first particle can take 2 joule of energy, the second particle can take 3 joule of energy, and the last particle can take 1 joule of energy. So the total energy of the system will be again 6 joule. So the algebraic form of this formula is given like this: energy of the system is summation of Ni epsilon I, where this represent the number of particles with same energy, and epsilon represent the energy of the particles. So what is the macro state of the system? So macro state of the system is specified by the N, V and E, where N is the number of particles, V is the volume of the system, and E is energy of the system. We can have different possible configurations like NV, or we in place of E we can have T temperature. So there is nothing to worry about it. But in our example we were discussing only about the N, V and E. So all they represent the macro state of the system. And each such way of achieving a particular macro state is called micro state. As you see in the example, there are we have one way, we have three ways, or we have six way of achieving the same macro state of 6 joule. Okay, so what is microstate? So microstate is the way of achieving a macro state. Like we have one, three, or six microstates for our particular system. So we will represent microstate by omega, and omega is written as omega as a function of n, v, e, or as in case of our example, we are only concerned with the energy E of the system, so it can be written like this. So I hope everything is clear to you for of this lecture. Now, from next lecture, we will study about the classical form of statistical mechanics, where we will discuss how classical mechanics is used to find the position and momenta of particles, or the atoms in the system. And from these position and momenta, how we can calculate the properties of the system like pressure, temperature, volume, whatever we want to calculate. So we will study this from our next lecture. Thank you.